In this video, we're going to see how we can understand the number of valence electrons in different atoms, which is to say the number beyond the noble gas configuration, and how this number of valence electrons is going to be very intricately intertwined with an atom's ability to participate in covalent bonding, that is the sharing of its electrons in order to form attachments to other atoms in what we call covalent bonds. We're going to see how we can draw what we call Lewis structures of these molecules and show their general structure, connectivity, how we can assess if these are good or bad Lewis structures, all based on the valence electrons and the general rules that we're going to learn for drawing Lewis structures. Because knowing how the atoms within a covalent molecule are connected is going to tell us a lot about other properties of that molecule, as we're going to see in future videos. So again, how to draw a correct Lewis structure, how to understand what the Lewis structure represents, and just how to understand covalent bonding a bit more in general will be the focus of this video here. And without much more, let's jump in. All right, so we've learned quite a bit about valence electrons and therefore about how many bonds these various elements, atoms, like to form when they're in covalent bonds, covalent complexes, right? Because the idea is that these atoms want to have access to generally 8 electrons, notable exception for hydrogen, which only wants to have access to 2. And this really follows with the idea that atoms want to be like noble gases, right? The end of this period that has carbon, nitrogen, oxygen, fluorine is neon, which has its 8 valence electrons, right? Its complete shell. And so the motivation for all of these different atoms is to have that complete shell as well. But of course for hydrogen, gaining 1 makes it like helium, so its complete shell is 2 electrons. And so this I think is a very useful chart, and it does apply down the group as well, meaning below carbon is silicon, and that one also generally wants to form 4 bonds. And really, these ones have quite little exception to these ideas, right? We'll see that there are some more exceptional ones coming up, but in general, carbon, nitrogen, oxygen, and fluorine will find their most stable Lewis structures with the following number of bonds. And that is to say that carbon has 4 valence electrons and wants 4 more, and therefore will form 4 bonds, having no lone pairs remaining. And this number of lone pairs is very important to consider as well. It would not be at all a correct answer to draw one of these structures and forget that there are lone pairs there. We'll see just how important they are when we turn our attention towards geometry as well. And keep in mind that the most important thing for all of these structures we're going to draw is that the total number of electrons absolutely must be adhered to. And so for an example here, we can take a look at NH3, and what we see is that we have a central nitrogen that likes to make 3 bonds, right? It bonds to each hydrogen once. The compound is NH3. This is called ammonia. Nitrogen has 5 valence electrons, and therefore, because it's sharing 3 of those, it'll be left with a lone pair, and that's kind of that favored configuration that we took a look at on the previous slide. Now, what about the total number of electrons, right? Well, it has 8 total electrons, and this is the 5 valence electrons on nitrogen, plus 1 valence electron on each of these 3 hydrogens, which makes 8 total electrons. And as we count up our Lewis structures, electrons that are present, we see that there are 3 bonded pairs denoted by the lines. This is 6 electrons plus the lone pair on nitrogen, and therefore we've placed all these electrons, which is very important. All right, how about OF2? Maybe give this one a pause and see if you can draw this Lewis structure, or if you have it already, we'll verify in the next slide. But OF2, first of all, we want to count and make sure we are going to place 20 total electrons. This is the 6 valence electrons on oxygen, plus 7 on each fluorine. So 2 times 7 is 14 electrons, plus the 6 on oxygen makes 20. And so we want to make sure we're placing 20 total electrons. We know that oxygen with 6 valence electrons likes to form 2 bonds, and fluorine likes to form 1 because it's a halogen and is just 1 away from that complete octet. And so here is a proposed Lewis structure, right? It ends up being the correct Lewis structure. And we have oxygen in the center with the fluorines on the side. And that we have 2 bonds with the oxygen, 1 to each fluorine, and each fluorine, of course, has just the 1 covalent bond. Note that we also have all these lone pairs, right? So fluorine should have 3 remaining lone pairs because it has 7 electrons total and is only sharing 1. And if we count all these up, we'll do the lone pairs first. So 2, 4, 6, 8, 10, 12, 14, 16 lone pair electrons. And then there are 2 bonded pairs, so that's 4 more electrons, and there we have our 20 total electrons. Always make sure you count the total number of electrons before concluding that it's a correct Lewis structure. Because again, we absolutely cannot miss any electrons, right? There is no exception to that rule. It's the most important one. We got to place all of our electrons. Now we can draw Lewis structures for charged molecules as well. And we'll note that things may be a little different, but only because there's kind of an extra electron. So the idea is, how can we satisfy our octets? How can we make sure we place all of our electrons when we have this charge to consider as well? So when you're doing your total electron count, make sure that you count for the presence of this negative charge on each of these as well. Start with that, and then provide your Lewis structure, and then we'll go ahead and show the answer. But go ahead and pause and give that a try for now. All right, hopefully you were able to come up with something, right? So let's take a look at OH-. This is the polyatomic ion hydroxide, and we see it has 8 total electrons. This is the 6 valence on oxygen, 1 valence on hydrogen, plus the extra lone electron, making 8 total. And for OCH3, we have 14 total electrons. This is 6 on the oxygen, 4 on the carbon, that makes 10, plus the 3 lone electrons on hydrogen, that makes 13, and then the negative charge makes a 14th electron. And we'll know that, with this extra electron, we're able to have an even number of electrons, right? Without it, we would have an odd number, which we know we don't like. Electrons like to be in pairs, so the fact that this has the extra electron definitely doesn't mean there's a lone electron anywhere. It really is able to make them all pair up. And so let's take a look at the hydroxide first. This is our correct Lewis structure. Oxygen in this case is only going to be able to form 1 bond, but because of that extra electron, it's still able to fulfill its octet, right? That extra electron basically goes to oxygen, and then oxygen with its 7 electrons shares 1 with the hydrogen, and we still have our 8 total electrons in the end. Note that when we have charged molecules, we really want to put brackets around the molecule with the charge on the outside. Very important. For OCH3, we want to kind of follow the same rules, right? How many bonds does carbon like? How many does oxygen like? And where is that negative charge going to need to go, right? And so this may take a little bit of, finagling, but, do just try something to start, right? Start with carbon in the middle, likes the most bonds. That's a great place to start. And it is in the end the right answer, because what we can see is that we have carbon in the middle making its 4 bonds as usual. Carbon is probably the most rigid of all of these molecules or atoms, right? Because oxygen, we'll see, will take this negative charge making 1 bond. But carbon really just wants to have 4 bonds and really doesn't like to have an extra lone pair. So anchoring your structures with carbon in the middle is always a good approach. Here we have carbon in the middle, 3 hydrogens bonded to it, oxygen also bonded to the carbon, and if we count our electrons, we'll start with the bonded pairs, so there's 4 of them, that's 8 electrons, plus the 3 lone pairs on oxygen, which is 6 more to make 14 total. And there we have our Lewis dot diagram for this OCH3 as well. Okay, note that we can also have multiple bonding, right? Sometimes there aren't enough atoms for one atom to bond to, because we know carbon likes to have 4 bonds. So how can we accomplish that? By adding additional bonds, right? Sharing multiple pairs of electrons. And go ahead and do your electron count for both of these, and then try to start with a dot diagram. Just give it a try, right? Know that the one that wants to make the most bonds will probably be in the middle. And know that if you do start on the wrong track, it should be pretty apparent before too long, right? That you're not going to be able to fulfill your octets very easily, and all that. So these all do work out pretty well in the end. So just go ahead and give them a try, pause the video, and see what you come up with. Alright, so we'll start here with CO2. This is carbon dioxide, and it has 16 total electrons, 4 for the carbon, 6 each for the oxygens. That's 12 oxygens. Oxygen electrons plus 4 is 16. HCN, here we have 10, and this is from the 5 on nitrogen, 1 on hydrogen makes 6, plus the 4 on carbon makes 10 total. And so how can we do our electron structures, the Lewis dot diagrams? Well, we know carbon likes to have the most bonds, so let's start with carbon in the middle. And if we do that for CO2, maybe we start with something like oxygen, single bonded to carbon, single bonded to oxygen. That's only 4 of our electrons. And then we can go ahead and place our lone pairs, but we realize the octets aren't quite full, and we'll have an extra electron on each of the oxygens. And so in the end, in order to fulfill our octets, we know carbon likes to make 2 bonds, carbon likes to make 4 bonds, oxygen likes to make 2, and therefore we're going to have sharing of multiple pairs of electrons, carbon and oxygen. For the HCN, we know that nitrogen likes to have 3 shared pairs, carbon likes to have 4 shared pairs, and nitrogen will take its lone pair, and so we end up with a dot diagram that looks like this. So yeah, multiple bonds can definitely make it so the sharing is permitted and is definitely something to consider when you have non-hydrogen atoms. Is it necessary to make multiple bonding? All right, as we may know or may not know, there are some exceptions to the octet rule, and these exceptions come in 2 forms. The first is in number 1 here, and that is when there simply aren't enough electrons to make an octet. So how can we make a Lewis structure for BH3 that accommodates that? And the second one is that once we're in the period 3 and below, we are able to have what's called an expanded octet, where we are able to have elements that can take more than just that 8 electrons, right? Because they're getting close to those d orbitals, they're able to accommodate more than just the octet's worth of electrons. So go ahead and count the electrons, give this video a pause, and we will discuss the results for each of these. Alright, so let's start with BH3. If we count our electrons, there are 3 on boron valence plus 1 for each of these 3 hydrogens, so 6 total electrons. And if we count this sulfur hexafluoride, we'll see there are 6 valence on sulfur, 7 valence on each of the 6 fluorines, and so that should give us 48 total electrons, right? 42 is 6 times 7, plus the 6 on sulfur gives us 48. And so how do we do boron tetrahydride to start with, number 1? Well, it's only got 6 total electrons, so unfortunately our Lewis dot diagram is going to look like this, right? We're not going to be able to have a full octet on boron, because remember the most important rule is to place all the electrons and no more. So it simply won't be able to have a full octet in the case of BH3. How about SF6? Well, remember, fluorine really only likes to have 1 bond, and so it's going to look something like this, right? Where fluorine still just wants to have that 1 bond. This is really very characteristic of the halogens. They just want 1 bond with 3 lone pairs. But being a period 3 element, sulfur is able to have what's called an expanded octet because it can access those d orbitals that are really just a few electron energy levels away. Oxygen is not close enough, right? And so that is just way too far above where oxygen holds its electrons, and therefore, even though oxygen is in the same group as sulfur, OF6 does not exist because it's not able to access this expanded octet.